Okay, so good morning, good afternoon, evening, everyone. Welcome. I'm Anhil Zhang from Yonsei University, and I'll be moderating today's session. Today's session is being recorded. Please keep your microphone muted while the speaker is presenting. Hold all questions until the Q&A at the end. Feel free to type in the chat. I'll read those questions aloud. It is really my big pleasure to introduce the speaker today. Professor Vlatko Vedral got PhD and BSc at Imperial College, and he is a professor at Quantum Information at Oxford. He has published over 400 research papers on various topics in quantum physics and computing, and he is one of the Clarivate highly cited researchers. He has given numerous invited talks at Solovay Meeting 2010, and a popular one at the International Safe Scientific 2007. He was awarded the Royal Society Olfson Research Merit Award in 2007 and the World Scientific Medal and Prize in 2009, the Marco Jarek Award in 2010, and was elected a Fellow of the Institute of Physics in 2017 and a member of the European Academy of Sciences in 2020. He is consulting the World Economic Forum of the Future of the Computation. He is the author of the 4 textbooks and 3 popular books, Decoding Reality, From Micro to Macro, and Portals to a New Reality. He gives regular interviews to the media and is actively engaged in popularization of physics also by writing for New Scientists, Scientific American, and major UK and overseas newspapers. Please join me in welcoming Professor Vlatko Vedral.
Thank you very much. It's my big pleasure to be talking to you, and thank you for the kind introduction and for the invitation to speak about this topic. It's a very broad topic, and I won't be able to cover all of these things in great detail. So please ask me questions at any point, and I'm happy to engage in a discussion. So I think what I will present is maybe not a majority view. And the reason why I feel that I should list all of these things that people traditionally think are problems when we are trying to unite quantum physics and gravity, whatever this may mean to unify the two theories, people frequently come up with a list of problems. And the reason why I think that I'm in the minority in some sense is that I think that if you look more deeply into any of these problems, you will realize that they are not really problems. In a sense that there are no bigger problems than what we face in standard quantum field theory. So for instance, equivalence principle is not a problem, according to my view. And I will talk a little bit about this. I will expand on what I have in mind. Entanglement is not a problem. I think if you think of gravity as being a fully classical theory, something that is never quantized, you will of course encounter problems with the superposition principle, with the uncertainty principle, and ultimately with entanglement. But if you think of gravity as a quantum mechanical entity as well, then entanglement really represents no problem at all. Sometimes people talk about gravity being a field on itself, in the sense that the gravitational field is encoding space-time. And so people think that it sounds very unusual that I should have a field which is a function of space-time, but space-time is the field itself. And I think this doesn't really represent a problem either. You will hear people talk about non-local observables, which are needed for gravity. And I don't think that this is a particularly unique problem to gravity. As you know, the simplest gauge theory, electrodynamics, already has an issue with gauges. And I don't think this requires us to talk about non-local observables. I think it's straightforward to talk about local entities that we measure, and I don't think we ever need to violate locality. Then you will hear people talk about the time problem, the measurement problem, and again, I don't think these are problematic, and they're certainly not more problematic in gravity than in anything else than we are facing. And something that possibly could be uniquely gravitational is this last bit, which is about nonlinear interactions. Sometimes people call this in a very colorful way that gravity gravitates, which means that the gravitational field acts on anything which has energy. And because the gravitational field itself has energy, then basically it should act on itself, which means that it's nonlinear. In a sense, this is unique to the gravitational field, but these kind of nonlinearities of a similar kind occur when you couple things in other field theories. So I think this will occur also in electrodynamics once you couple matter to the field. And it seems to me that what we are facing in gravity is no different really as far as these difficulties. But I won't be talking about that because my talk will focus on understanding what happens in the linear regime and asking whether we can even test the linear regime. So speaking about testing quantum gravity, it's very helpful to look at this physics cube, as people call it. So you've got the three fundamental constants there. You've got the G Newtonian gravitational constant, you've got H bar signifying quantum effects, and you've got the speed of light. Here, maybe easier to think of 1 over speed of light because as the speed of light goes to infinity, this limit is basically classical, the classical Newtonian mechanics limit. So if you look at this cube, and if you think about all of the three constants being important, we are talking about this vertex that's the closest to us, which I labeled as the theory of everything. Of course, we don't know if this is the theory of everything. There may well be that something comes beyond unification of quantum mechanics and general relativity. But for the current purposes, this would be the point where we have really unified gravity with all of the other forces, and we have the theory of everything as far as the current state of affairs is concerned. But we certainly haven't tested experimentally anything in this domain. But even if you look at the domain where we are non-relativistic, but still G, Newtonian gravitational constant, and H bar cannot be ignored. This is what I call the non-relativistic semi-classical regime, this vertex here. If you think about it, we haven't tested this vertex very much either. So I think rather than talking about the conceptual problems that are there, which I don't think, like I said, are more problematic than anything else we are facing in field theory, it seems to me the biggest problem for us is that we haven't really tested the domain where quantum physics and general relativity matter at the same time. And that's really the biggest challenge to us. We don't even know what kind of outcomes we will have, even in the simplest of these kind of cases. So what I listed is that we tested, for instance, a single neutron interfering in Earth's gravitational field. That's the famous cow experiment that I mentioned here. These are Colella, Overhauser, and Werner, three physicists who did these tests in the 60s and the 70s. But in fact, this is a fully semi-classical regime. And we know that nothing goes wrong, of course, with either quantum physics or gravity at that point. But we haven't tested any other semi-classical results. You must be familiar with the Unruh effect, with the Hawking radiation. All of these are results that are done not within the full quantum gravity theory, which of course we don't have, but they're done in the semi-classical regime. And because of the conditions that are required for them to be tested, we haven't been able to reach this degree of sophistication either. And so I want to spend a couple of slides on why it's so difficult to find a domain where both quantum mechanics and gravity matter at the same time. And maybe the easiest way to understand this is to look at something that's called the gravitational fine structure constant, if you like. It's the analog of the electromagnetic fine structure constant, which I call alpha here. And this is a constant that very loosely speaking, tells us how strongly matter and light and the electromagnetic field couple to one another. And the value is this famous number 1 over 137 and some corrections there. So I'm giving a rough estimate of the order of magnitude of this. However, if you compute the gravitational analog of this, you will actually get a quantity that's 43 orders of magnitude smaller. So, and that really tells us why we have difficulties. And in very simple language, it's because gravitational forces are simply the weakest forces that we are aware of at present. So if you do a very simple calculation of the following kind, if you ask yourself, you excite an atom, let's say you excite the hydrogen atom. You shine some laser light and you move the electron from the ground to one of the excited states. And you ask yourself, how quickly will this electron spontaneously go back to the ground state and emit radiation? Then you can use a very simple model in electrodynamics to calculate that. If you use the same model in the linear gravitational approximation, which in this case is sufficient to give you a good estimate, an extremely accurate estimate of how long it would take the electron to de-excite and emit a graviton instead of a photon, you will get a quantity that actually is proportional to the gravitational fine structure constant. This has been computed by many people. I'm listing here people like Weinberg in his beautiful book on general relativity. Many papers are there. Dyson may be one of the more recent people to do various calculations in this direction. And you can now compare gamma, in this case, gamma electromagnetic with the gamma gravitational. And as I said, the electromagnetic gamma is proportional to the fine structure constant, whereas the gravitational gamma is proportional to the gravitational fine structure constant. And so basically, if it takes the hydrogen atom a nanosecond to emit a photon, then it would take 43 orders of magnitude longer to emit a graviton, which of course is much longer than the age of the universe. So basically, it's extremely unrealistic, and many of these people that I cited have pointed this out. It's extremely unrealistic to think that anytime soon we will be able to construct graviton detectors and detect gravitons and do tomography of the gravitational field in the same way that we are doing tomography of the electromagnetic field. And this led many people to conclude that we are not even able to test the regime where quantum mechanics and general relativity come together. Some people have concluded from this, Freeman Dyson in particular, that actually maybe we will always have to use quantum mechanics and classical general relativity in completely separate domains, and there is no domain in which is feasible to test them together. And for the rest of my talk, I want to actually challenge this kind of view, and I want to explain that we could test the quantum nature of the gravitational field even now with the present technology, without having to detect gravitons directly. And I think that's maybe the surprise. But before I get there, I want to take you back in history to the Chapel Hill Conference in 1957. You can read the transcript of this conference, and there is a famous discussion between Feynman and many other people at that conference. The conference was exactly on the topic of quantizing gravity and what does it mean to quantize gravity. And at that meeting, Feynman suggested that we must somehow be able to address this question, how to proceed, because if we put a single mass in a superposition of two different places, as I have in this picture here, in one place and the place that's a distance, a meters away from this place, then in each of these places separately, the mass would affect the gravitational field locally, just as it would happen with the electromagnetic field. We have the perfect analog in electrodynamics. And the question now is, how will gravity couple to this superposition? But the point I want to make here is that this experiment is not enough for us. If you have a single mass in a superposition, and if you're able to bring it back and to interfere it, this doesn't really prove anything regarding the gravitational field. Here, the way I'm putting this is, imagine that you couldn't perform interference with an object of a certain size and bigger. If you conclude that you will never get interference of objects that are more massive than a certain object, that does not allow you to conclude that gravity is not quantum mechanical. And that's simply because we know that a quantum mechanical field can perfectly well act to decohere the superposition of the mass, which is exactly what I'm writing in my equations. I'm imagining that the mass is sitting in a superposition of x and x plus a, and then I'm imagining that the field is sitting in some coherent state. Let's say it's the best classical representation of a field. And what can happen when you make this superposition is that the gravitational field becomes entangled to the mass itself. And if it becomes entangled enough to the mass, when you trace out the gravitational field, the mass will basically be in a mixed state. You will never be able to detect any interference with the mass in this experiment. So actually, if you were to perform an experiment with a single massive object, you split it into a superposition, you re-interfere it, whether you managed to interfere it or you didn't manage to interfere it gives us no information ultimately about the gravitational field. You would have to do something else on top of this to be able to really probe the nature of the gravitational field. And I will get there in about 10, 15 minutes time and tell you about that. Now, even though a single mass doesn't really suffice to probe the quantum nature of the gravitational field, you can still do some interesting experiments with that, because people believe, as I was saying in my very first slide, that there are already potential problems even with a single mass. So there are things that we could test, and we have been testing, and I'll tell you about one of these tests. Whether even the equivalence principle of general relativity is in conflict with a single massive superposition. So remember, what the equivalence principle is telling us is that acceleration and gravity cannot be discriminated locally. They're indistinguishable. There is no experiment that can tell us if we're sitting in a lift. That's the famous example that Einstein had, falling inside a lift. He called that the happiest thought of his life when he realized this idea. If you're sitting inside a lift and you feel that you are stuck to the bottom of the lift, you cannot tell. There is no experiment you can do inside the lift to tell you whether someone is pushing the lift and accelerating the lift, which is why you are stuck to the floor of the lift, or whether you're sitting, the whole lift is sitting on top of a massive object, which is why, again, you feel exactly the same force holding you down to the floor of the lift. So that's what the equivalence principle says. And the question now is whether this equivalence principle is in conflict with having a superposition of two different accelerations. So how should I apply the equivalence principle if I have an object which exists in two different states, and in each of these states it's accelerating at a different rate? So actually, Chiara Marletto and myself thought a lot about this problem. We wrote several papers. I'm mentioning one of them about 5-6 years ago, where we argued that there shouldn't be any problem with superposing inertial and non-inertial motions. So, for instance, if you have zero acceleration, if you have inertial motion, and if you have something that's accelerated in Earth's gravity, let's say, this should actually be able to exhibit quantum interference. And that's the question now, because these things have not been tested with more and more massive objects. The question is, does the equivalence principle generalize to quantum superpositions? And I think my point here is that there is no reason why this shouldn't be the case. And so I imagined a very medieval, almost medieval kind of experiment, something that Galileo would have liked. I think you know that he was dropping, well, that's the myth, that he was dropping things from the Leaning Tower of Pisa. I think he was dropping things down inclined planes, and he was observing their motion and their acceleration. So I imagined this kind of test, that you generate a massive object in a superposition of a constant velocity motion. This could be like your reference branch of the superposition. And then you have another branch of the superposition in which the object undergoes ballistic motion in Earth's gravity. And the question is, will these two states be able to interfere ultimately and show the usual quantum mechanical interference fringes? And we talked about this meeting, Chiara and I, at various places. And I think at one of these meetings, we had Roger Penrose attending, and I think his intuition is in the opposite direction. He feels that, I think, gravity will somehow prevail over quantum mechanics, and that the classical equivalence principle will somehow act as a mechanism to collapse quantum superpositions. So we had this very lively disagreement between us, which still goes on. And luckily for us, there was an experimental physicist in the audience called Ron Folman, an Israeli experimental physicist. And so he said immediately, I'm going to do this experiment. I think this is an interesting idea. I'm going to try and test it. And so this is a very simple picture. What he did is he has cold atoms, Bose condensates, on a chip. So this is a very, you can see that this is a square with very tiny dimensions, this chip. It's basically 100 microns or so. He can trap a condensate there, and then he can launch it using a carefully designed magnetic field. he can launch it in a way that it goes in a superposition of a ballistic trajectory and a trajectory that's moving uniformly. It doesn't accelerate, which is called the reference wave packet. So the whole massive condensate wave packet splits into two. And then when the ballistic motion ends, the two unite. And the question is, what kind of result are we going to get there? And so this is a paper that is recently been published, I think, in Science Advances. We've had lots of theoreticians arguing about the results, and I'm very happy to report that actually we do observe interference fringes here. There's absolutely no signature here that gravity collapses any of this kind of massive superposition. Of course, we are still talking about a very, very small condensate. We are talking about 10,000 atoms present in this condensate. And one could always argue that as you make these condensates larger and larger, at some point something may happen that will disrupt quantum superpositions, that will collapse quantum superpositions. But we are not there yet. And as I said a few slides ago, even if something collapses at some point for a massive enough object, this will not allow us to conclude anything about gravity. It could still be that gravity is quantum mechanical, and that through entanglement, through getting entangled to the condensate, it basically achieves the same thing. So somehow not being able to interfere could also be a proof of the quantum nature of the gravitational field. So one mass is not enough. Now, let me tell you about the second version of the equivalence principle. And that's the one that Chiara and I proposed in 2017. So the question here is to use again the principle that acceleration and gravity are locally indistinguishable, but to ask the following question. If I have a superposition of a massive object, like in the previous case, but I take another quantum object as a test mass, the question is, how will this object respond to the superposed mass? So here is a massive object in a superposition. You can again think about a condensate. Condensates are not big enough. I will tell you what we think will be the best to test this. Take a wave packet in a superposition of two places, put in another wave packet a certain distance away, and the question is, how will this wave packet be attracted to the original wave packet? And what we think, and that's because we think that gravitational field will turn out to be quantum mechanical, that's what we are betting on, is that this test particle will simultaneously accelerate towards one of these centers of the superposition and the other center simultaneously. So just like what we had in the previous slide, that we had two different accelerations superposed, in this case, the test mass will end up accelerating simultaneously in two different ways. It will basically become entangled to the original mass that generates the electromagnetic field. So this is, I think, what it would mean for gravity to be fully quantum mechanical. And I think the principle that really guides us in this is a principle that was used a long, long time ago, possibly the first time by Heisenberg, to argue that the electromagnetic field must also be quantum mechanical. Because remember, after Heisenberg came up with quantum mechanics in 1925, already in 1926, 1927, people started to work out how one would quantize the electromagnetic field. And Heisenberg gave beautiful arguments why one must quantize the electromagnetic field. And the argument was very similar to Feynman's argument, I think. It was simply to take a charge, put it in a superposition of two different places, and ask what kind of field does this generate? And Heisenberg argued that the only consistent way of treating this is to quantize the electromagnetic field itself. If you couple a classical field to a matter superposition, to a charge superposition or a massive object superposed, you will almost invariably end up violating some of the key principles. You will violate the Heisenberg uncertainty principle, which is what bothered Heisenberg himself. But in fact, if you analyze this even more carefully, you will end up violating all sorts of other symmetries like conservation laws, like energy momentum conservation, that we think are fundamental and upheld exactly. And I mentioned here that the argument that Heisenberg had was ultimately made famous by Schrödinger himself, of course, who talked about Schrödinger's cat. And the point for him was that anything that can couple to a microscopic superposition must itself be able to join that superposition, no matter how macroscopic that object is. So that's the intuition that's guiding us here. And so what Chiara and I proposed, and it was independently proposed by Sugato Bose and his team, was instead of taking a single massive superposition and testing what happens in the gravitational field, take two massive superpositions in parallel. They have to be nicely collimated. So basically, the pictorial representation here is really like two Mach-Zehnder interferometers that are running in parallel. So each of these masses is put in a superposition of states, and then each of these elements of the superposition can in principle gravitationally couple to any of the other elements of the superposition. And that's what this is testing. Will gravity be able to mediate interaction between these two superpositions in the fully quantum mechanical way? Or if gravity still remains classical, and some people think that this might be the case, then this will not be possible. You will not be able to mediate all of these interactions simultaneously. So we came up with this witness of the quantum nature of the gravitational field, which says that if a system can induce entanglement between two other systems by acting locally, just like any field does, acting locally, then that system itself, if it has the capacity to entangle, it must be fully quantum mechanical. It must have enough quantum mechanical degrees of freedom at that level to produce that entanglement. In the technical jargon, it must have non-commuting elements of reality. It must have non-commuting observables which need to be used in the description for this to work. So there are many ways of proving this, but I think most of you, and I think it's very much appropriate for your series, I actually prefer the information-theoretic approach to this. And I think quite a lot of these ideas that I'm presenting really do come from quantum information. This is bread and butter for quantum information because we think about all of the fundamental systems as being equally capable of encoding quantum information. So we are talking about universality, according to which it doesn't matter whether you're using a photon or you're using an electron or you're using an atom or you're using a more complicated object. All of these objects are capable equally. Of course, some of them may be experimentally more difficult to manipulate than others, but in principle, they all can hold and manipulate and transfer exactly the same kind of information. So I want to give you the flavor of this proof. It's a very simple one, and you can read more about the details in this paper that I'm citing here. Also, our recent reviews of modern physics, I think, will talk about it in great detail. But the idea is that if I want to communicate information between two systems A and C via another system B, so A can only couple to B and C can only couple to B, but A cannot directly couple to C. The question is what kind of correlations can I create between A and C? And so we have a very general proof where we are assuming that if B can only handle classical information, but A and C can handle more than classical information. This is something that Chiara calls super information media. So they are media that can go beyond classical information. Then basically what you can show is that if B can only manipulate classical information, it can never create the super correlations between these super information media. And the proof is very similar to what is known as data processing inequality. So if I start with information in A, then I process it by going to B, and then for B, I process this and store it in C, then the information, the mutual information, the correlations between A and C can never be bigger than the mutual information between A and B. And that's the key point here. So if B is purely classical, then the mutual information between A and B is simply classical. And whatever you transfer from B to C cannot magically become quantum mechanical. So A and C can then at best only be correlated classically as well. So in other words, if you discover that A and C are more correlated than classically, let's say they are entangled like with quantum systems, then you must conclude from this information theoretic argument that B must also be capable of processing quantum information. Otherwise, this wouldn't work. So back to the experiment, just to show you what kind of entanglement is produced between these two superposed masses, you can simply do a very simple, very basic Newtonian calculation where the phase between the closest branches is the only one that I take into account, and to a first order of approximation, I'm ignoring all the other phases. And if you look at what happens to the initially superposed state of two different qubits, it basically becomes a controlled phase gate. And if you wait for the right amount of time, which you can see from this formula, so that the phase is maximum equals to pi, then basically you've created a maximally entangled state between the two. So when one mass is in the branch 0, the other mass is in a positive superposition of the two states, 0 plus 1. And when the first mass is in the branch 1, the second mass is also in a superposition with a negative phase between the two. So this is equivalent to one of the maximally entangled. It's a rotated maximally entangled Bell state, if you like. And if you manage to detect something like this in an experiment, it would be a definitive conclusive proof that gravity must have quantum mechanical degrees of freedom, providing that gravity acts locally, providing you don't allow the masses to couple directly, but only through the gravitational field. So that's the key assumption here. And this is just to give you roughly an idea how difficult this experiment is. Initially, I think we thought about a nanogram. We did slightly more careful estimates, and I think we can go 3 or 4 orders of magnitude below this. But it's still a very challenging massive objects. We're talking about masses that are 10 orders of magnitude bigger than anything that's been interfered in the laboratory so far. But people are working on this, and I think there are 5 or 6 groups now competing to realize this experiment, and that gives me a lot of optimism that I think we will be able to get there sooner rather than later. Obviously, the main difficulty with this implementation is to try to isolate the system well enough that it can remain in this entangled state in a superposition for long enough that you can actually detect the maximum entanglement without any environmental negative influences on top of it. So that's a big challenge, of course, and the challenge grows the more massive the object is. So let me return to physics now. What could this mean? What elements of the gravitational field would become quantum mechanical? And you can actually run at this level a very similar theoretical argument to the one that Heisenberg, like I mentioned, did a long time ago. And what would happen at the level of, if this is the way that gravity works, we don't know. That's exactly what we need to test. But if it really behaves in the linear regime like the electromagnetic field behaved, then the metric tensor G mu nu would actually act like the vector potential in the electromagnetic field, and the Christoffel symbols, the gravitational field, would act like the electric and the magnetic field components, like the Faraday tensor, if you're thinking about this special relativistically. So basically, the same way that in electromagnetism we cannot measure the vector potential at the same time to a desired degree of accuracy as the electromagnetic field itself, in gravity, you could not measure the metric and the field components, the Christoffel symbols, to the same degree of accuracy. So much like the electric and the magnetic fields, when they become quantized, they become operators and they no longer commute. In the same way, different components of gamma would actually be upgraded to quantum mechanical observables and they would not commute. So that's really what we are testing. I think there's a very beautiful paper, very short paper by Perez, Asher Perez and Nathan Rosen from 1960 in Physical Review, which actually talks beautifully about these analogies. Of course, they didn't offer any way of testing that. They just showed the theoretical analogy between the two. So like I said, it's extremely challenging to do these tests, and I'm happy to tell you more about it if there are questions. Here is one paper that we put out recently where we suggested NV centers and doing a Stern-Gerlach type of experiment by trapping one of these color centers, magnetically trapping it, and then utilizing a spin degree of freedom in the vacancy to create a superposition of the spins, which then would allow the magnetic field to create a spatial superposition of this massive object. And actually, these objects could be as massive as you like them to be. They certainly could be on the order of the nanograms or a few orders of magnitude smaller, which is what's required for this. The difficulty, obviously, is to keep two such interferometers very close to one another so that gravitational interaction is strong enough, and then keeping both interferometers for long enough. And when I say long enough, we are talking about seconds. So it's very challenging. It's taking an object of the size of a nanogram, splitting it in a superposition of the size of about 100 microns, and keeping this for about a second long in this kind of superposition to build up maximum entanglement. And that's, of course, extremely challenging, but that's what we require. I'm citing another paper here just for fun to tell you that we don't need to think necessarily just about lab-based tests. This is a test that we thought about, which I think ultimately is inappropriate. The numbers are just they are not suitable to test gravity. They're too small. But you can think about double beta decay, and you can think about neutrino oscillations, which give you a very similar setup to the one that I told you about. Of course, this would be an experiment in astrophysics, not an experiment in the lab. But I think if we get creative, we will think about many different platforms in which this experiment could be realized. And that gives me even more confidence, like I said, that within probably 5 years or so, we will have our first answer as to whether gravity has some quantum mechanical degrees of freedom. And that's extremely interesting to me. So a couple of last things to mention. This experiment will tell us whether gravity has quantum degrees of freedom at the lowest level, but it won't tell us which of the canonical approaches to gravity is the right approach. There are many canonical approaches. There is, for instance, loop quantum gravity, which is different to the approach that I was discussing here of Perez and Rosen and what Feynman did, which was similar to that. Then, of course, we have string theory, which in this regime would completely agree with all of these approaches that I call canonical. And I think all of these approaches would basically agree that entanglement and the same amount of entanglement would be established between the two masses. So if we want to discriminate, they would all pass the test, but if we want to discriminate between them, we would have to think about the next experiment and what else to test and going to the next order of magnitude, which is something that I'm thinking about at present. So while people are developing these experiments, I'm really interested to think about what is the right way to quantize gravity and what exactly are the degrees of freedom that are quantum mechanical, and how would one test whether space-time needs to be quantized or the components of the field need to be quantized or anything else needs to be quantized. The good news is that the generated entanglement would rule out all the semi-classical models and any collapse theory. So as I said, I already know from speaking with my colleagues like Jonathan Oppenheim, Roger Penrose himself, that they think that this experiment will not generate any entanglement. And that's because two of them, they have very different views of gravity between two of them, but both of them agree that gravity will remain classical. And that's in contradiction, like I said, with my own views and views of many other people. So anyone who works with quantum field theory in curved spacetime will not be able to predict any entanglement. And if entanglement happens to be detected, all of these approaches would be ruled out. So this would be an extremely useful test for us. So just to show you another final experiment that might be slightly easier, and then I will conclude than the experiments that I've just outlined. There's a very cute application of this kind of experiment, which in a very strong sense I'm calling anti-gravity. It's not really anti-gravity. We can't get anti-gravity, but it's a post-selected anti-gravity, which again is only possible quantum mechanically. If gravity was classical, you couldn't do that. So this is the latest paper with my colleague Pablo Saldana and Chiara Malletto as well. So what we thought is, let's put a probe to be localized initially, not in a superposition, and let's have the source in a superposition. So this is very much like one of the pictures that I showed a while back. And if you prepare this source in a particular superposition, but measure it in a different superposition, then you can put different weights on different elements of the superposition, on the branch A and the branch B, so that when you average these two weights in that branch of the outcome, your probe has actually moved slightly to the left instead of to the right towards the source. So it's very interesting quantum mechanically that conditional on the outcome, which means if you post-select and you ignore all other outcomes of your measurement, you can actually get one of the masses to be repelled by gravity instead of being attracted to the other mass. And we thought that this is really a fun way to test the quantum nature of gravity, and it's only possible if you assume that gravity affects the probe simultaneously from the mass location A and the mass location B. Unless you assume quantum mechanical superposition of these two actions, you will never be able to get anti-gravity. So I thought this is a fun example. In all honesty, it's not clear that this experiment is less challenging than the experiment with two massive superpositions. I think the analysis that we did in the paper that I'm citing here suggests that this probably is equally difficult to the other one. So it's really neither here nor there. Um, but it's just for some implementations, it could be easier to not to have to superpose the second mass. But then, of course, you must be able to measure this mass very well and discriminate between different locations of that wave packet, which is now where the challenge for this experiment lies. So let me conclude with this because I've gone through many of these aspects, and I think I did very quickly. So I'm sure there will be questions. So my view is that general relativity is not incompatible with quantum mechanics. Nothing at present tells us that it's not. Maybe the experiments will surprise us, and it will be very interesting if they are not compatible. We will have to rethink foundations of physics very much in that case, but it seems to me that nothing at present suggests that. What you have to, of course, do with the gravitational field is you have to quantize it like we quantize anything else, in which case the elements of reality will not be just the classical C numbers, they must be the Q numbers. And the most exciting thing for me is that we can actually test these quantum gravitational effects in this linear regime, in the lowest order, in the Newtonian approximation of general relativity. And that's really great to be able to at least do some kind of test where both of these quantum mechanics and gravity matter equally. I already made a comment about nonlinear gravitational effects that we don't really need to worry about them at this stage. It's not clear that we need to worry about them ever. People mention that gravity is not renormalizable in the same way as the electromagnetic field and all the other forces. Like I said, to me, it's not clear really what happens at the next level of approximation. And the biggest challenge really still is how to get to that regime and how to design tests which are now even more sensitive to the next order of approximation, which of course is much smaller than the order of approximation we are discussing here. And that, of course, leads me to the final conclusion that we need many more ideas for different platforms how to test gravitationally induced entanglement. But I think, like I said, there is enough momentum here that we will have an answer sometime relatively soon. And I think it's a hugely exciting time for all of us in quantum physics. Thank you very much for your attention.